say, will be about solitons and probes in AdS-CFT. So we said a little bit about the idea of solitons. We said some soliton in the gravity dual should correspond to some soliton in the field theory. So let's say solitons. And the first soliton you can think of is the instanton. Well, I mean, I'm sure one can think of more, but I mean in 3+1 dimensional gauge theory. So for the instanton, this comes from the fact that the Euclidean action can be written as, well, as over there. So we can write it as F mu A F star or tilde mu A over 4 plus F mu minus F tilde mu squared. Sorry, over 8, yeah. All right, so yeah, then this is F squared. So from this term squared, we get F squared over 8. Then F tilde squared is the same as F squared. So we get, from the sum of the two squares, we get this, and then the cross terms cancel. But the point is that now we see that this is greater than or equal than F tilde. And the equality is for F equal to F tilde. So, sorry, F tilde over 8. And there's 1 over G squared in front. And this object is a topological index. So this is something that does not vary under small variations. And it's called either instanton number or by physicists or Pontryagin number more by mathematicians. For the equality, we have the BPST instanton. Whose quantum properties were found by 't Hooft. And this has the form written over there. So there's a set of matrices, constant matrices called 't Hooft matrices. Then 2 over G, x minus xi nu, 2 over G x minus xi squared plus rho squared. And then one can calculate the action of this instanton, and one finds that it is 8 pi squared over G squared. And it saturates that bound. So the quantum properties of the instanton were found by 't Hooft. And so this is a solution in Euclidean space. And so in Euclidean space, we can write a probability that, so like all probability of transitions between two different states would be a path integral. And in the classical limit, or well, in the, I mean the semi-classical limit in is given by just the exponential of minus the action, because the instanton action, as we see, is solves the equation of motion, and in particular is a minimum of all possible actions in this sector. So this probability of transition is between, let's say, state with winding number 1 and state with winding number 0. So you can say that at x4, which is Euclidean time, equal minus infinity, we have one winding number, and x4 is plus infinity, we have another winding number. So such that the variation of the winding number is 1, and the configuration that makes that transition of winding number is the instanton configuration. So at the quantum level, the instanton gives the probability to have a transition between states of different winding number. So this is in field theory. And then in gravity, this should correspond to some other soliton. And, well, so now we think, so this was here, when I wrote this was 3 dimensions, and this was 4 dimensions in the bulk, but now we think of the 4 dimensions on the boundary, and then 5 dimensions in the bulk. And so we want to have a soliton that corresponds on the boundary to the instanton. And this soliton is a D instanton. So so what does that mean? So the instanton is a solution that is localized in all 4 coordinates, right? So it's localized in space and in Euclidean time at an instant in time, hence instanton. And the D instanton is formally a D-1 brane, which means the same thing. So a DP brane has spatial extension in P spatial dimensions and time. So P equal to -1 means it's fixed also in time. So this would be a D instanton. Yeah, so the solution is given there on page 135. I will not write it down. So as usual, if I want to have a 1-point function of some operator, I have to vary the, so via the AdS-CFT map, I have to vary the on-shell supergravity action with respect to the source for corresponding to the operator. And so if I say the D instanton corresponds to some operator that is non-trivial for the instanton, then I vary the on-shell action, delta S, with respect to this source, phi 0. So here I mean variation with respect to the dilaton, so phi. So the D instanton has non-trivial, so as you see over there, has non-trivial e to the phi and another scalar, or pseudoscalar rather. So A. So these are non-trivial. And in particular, this is e to the phi 0 at infinity plus space dependence. And so if I vary with respect to this phi 0, I would get the 1-point function of the operator corresponding to phi 0, and that happens to be trace f mu nu squared. So yeah, with the variation of it's actually the action, so 1/2 g squared trace f mu nu squared. And then one calculates and gets the result written there. So 48, yeah, I may even write it, 48 over g squared Yang-Mills, z tilde 4 over z tilde squared plus x minus xa squared to the 4. And one sees this. I had, unfortunately, when writing it, when copying it here, I forgot to the power 4. So the point is, it's the same kind of, it's the same solution. So this, so well, no, sorry. No, this is A, not F squared. No, this was like this, but then trace F squared. Sorry, this was like this, but then trace F squared, trace F mu nu squared. Indeed, you take a derivative, you get the square of this, and then, so that's for F mu nu, then F mu nu squared is with the denominator to the power 4. And so it's actually the same as the one for the instanton solution. So that is a good check of what we are supposed to obtain. All right, so this is perhaps the clearest example where we can actually calculate things on both sides, and they are the same. Now, and also it was clear how to, it was very clear how to extend from instanton to de-instanton. But now let's consider another example, the baryons. So here I said a few words in the previous lectures. I said that so the mesons, while the mesons are things like Q bar Q, then the baryons are things with many Qs, specifically, so these are contraction with delta ij, so let's say contraction with delta ij, which is a group invariant of SUN. But then I can write down the baryon which has which corresponds to contraction with the group invariant epsilon I1 up to IN of SUN. So in this same notation, this would be QI1 I1, QIN IN, contracted with epsilon I1 IN. So for, in the case of actual QCD with a gauge group SU3, then I would have 3 Qs contracted with epsilon ijk. And so it's important to realize that we can define something non-trivial even in a theory like n equal 4 super m mils that has no quarks. So the Q's in here were quarks. But n equal 4 super m mils has no quarks. But I can add them as external objects. And we'll do this further when calculating Wilson loop. So external quarks means non-dynamical. And another way of saying it is they have very large, next to infinite mass. So if they have infinite mass, what's the non-trivial thing you could add? Well, you can think of adding, so these quarks each have infinite mass, but when I put them together in a baryon, if the thing is bound, if it's stable, that means that the total energy of the baryon is smaller than the energy of its components. So we interpret that as the presence of a baryon vertex. Okay, so we calculate the baryon vertex. And as I also said, there's a way to think of baryons as solitons by considering the low energy theory. So the low energy theory, so baryons are solitons in low energy QCD. So low energy QCD is described by the pions, which are the lowest mass particles in QCD. And so there's a way to describe the baryons as solitons in the so-called SCRM model. So in the low energy QCD, we have the pions, which are pseudo-Goldstone bosons for the breaking of an SU2 symmetry. Pseudo because they actually have a mass. If they would be a full Goldstone boson, they would be massless. And they have a mass. Why? Because the symmetry that we're talking about is not exact. It's an approximate symmetry. And if one considers the pions, let's say the pions together with the Higgs for the, so these are Goldstone bosons. If I consider the pions together with the Higgs, then I can put them into a matrix that transforms into SU2 cross SU2. And this is e to the pi times, how do I call it, tau? Or yeah, I think I call it tau, but they're Pauli matrices, plus I sigma. And since if I want to consider these as real scalar, as the actual scalar fields of dimension 1, then I have to divide by the pion coupling constant for dimensional reasons. And so the low energy action of QCD is written in terms of this U. And more precisely, we can write it in terms of U minus 1 du. that I call L mu. And so I can write a Lagrangian describing low energy QCD. Trace L mu, L mu. So this would describe just the low energy interactions of the pions and Higgs. But then, so this is just a quadratic term in L mu. And note that u minus 1 du is roughly speaking this. So L mu is the derivative of this. So this is like a kinetic term, d mu of the scalar squared. So this is, in some sense, the free action, a kinetic action. And then we would need to have some sort of interactions. And here, there are many possible candidates. Now, Skyrm considered that the interaction term is the commutator squared of L mu. So trace L mu commutator squared. And yeah, with some dimensional thing in front. It's called epsilon over 4, I guess. Epsilon squared over 4, just for dimensional reasons. But it's important to realize that actually, although Skyrm considered this interaction term as something natural, there are all sorts of possible interaction terms that all give the same result, that one has solitons that can be identified with baryons, solitons called skyrmions. Okay, and so yeah, so we can write down the we can write down a conserved topological current. Topological means that the conservation is automatic, right? So we can write down B mu equal the contraction with epsilon mu rho sigma, or B mu epsilon mu rho sigma, L mu, L rho with a trace. And then the charge B is when I put mu equal to 0, and then I'm left with integral epsilon I j k, trace L I L j k. So this is a topological charge, which means there should be a corresponding topological object that carries that charge. And that is the skyrmions. And so the way to understand this is the way to understand the fact that there's a topological index is to say that there is an SU2, which is the same as SO3 for the group. So the gauge group here was, so these were SU2 matrices. And the SO3 of special rotations. And so this charge is basically counting the number of wrappings of spatial rotations around the group, or group around spatial rotation. And the baryon is defined by the so-called Hedgecock configuration, where U is written like there, so the exponential of some function of R times n times tau. Okay. So this is, one can check afterwards that this has a non-zero binding energy, it's a soliton, and it has topological number 1. Well, with appropriate boundary conditions for f of r. So how do we understand then this object as a soliton in gravity? Well, so we said that strings have endpoints that are indices, Chan-Patton indices, that correspond to fundamental indices of SUN. So if I have a string, I have an I and a J like this. And if I consider then an external fundamental quark, how do I do this? Well, there's a simple way of doing it, which is to take this to infinity, all the way to infinity, right? And then this looks like a fundamental object. So the way you can think of this in terms of the D-brane picture. So in the D-brane picture, so this was in terms of the gravity dual, but in the D-brane picture, we had a number of D-branes on top of each other, giving us the gauge group SUN. And we can say we take one of them away, such that there are these long strings that start on one and end on the other. And so when I go close to the stack of branes on top of each other, in order to get AdS-CFT, what happens is that this string looks like this. So there's something that starts in the middle, but then ends all the way at infinity. Okay. So then how do I make a baryon vertex? Well, a baryon vertex, I said, it's a collection of n fundamental objects with the epsilon tensor. And the fundamental objects are strings. So they should be n strings ending on something. Right? At infinity, they are at infinity. But in the middle, they should end on something. And, well, on what can they end? Strings end on D-branes. So it has to be a D-brane. And so what we're getting is that we have n of these strings that start at infinity and end in the middle. And they should end on a D-brane. And one chooses a D5 brane. Why a D5? Because this can wrap on the S5. It has 5 spatial dimensions, so you can wrap on the S5. And so the rest of dimensions, so if I'm drawing here AdS5, these things look like a point. Okay? So this is the picture that we wanted to have. This baryon vertex looks like a soliton, but a particle, right? It has extension only in time, not in space. So, so that's the picture we're getting there. If I get a D5 wrapping on S5, then the spatial dimensions are taken care of, and we're left with just time. So this is a particle. And then the point is, why n strings exactly? And why not n-1 or whatever, some other number? Well, the point is that you remember we took, in order to obtain AdS-CFT, we took n d-branes on top of each other, which meant that there was the charge of the corresponding Ramond-Ramond field, the charge of, in this case, a self-dual 5-form field strength. The charge of this was n. So, so then, if I, so that means that if I want to compensate something wrapping the S5 at infinity, where it sees a charge, so the S5 is the S5 away from the d-branes, at infinity from the d-branes. So there it sees charge n. So this thing, this d5 brane on S5 would have a charge n, and so by itself would not make sense in order to, because you cannot have non-trivial charge on a compact space, right? The flux lines have nowhere to go. So the only way to do that is to compensate by adding strings which also each have charge 1. So that's basically, I mean, algebraically, it's what I've written in page 139. So that you get the integral of this 5-form field strength is n, and then the Wess-Zumino term on the d5 brane has this F5 self-dual multiplied by an A, which is the gauge field on the d5 brane. And so when I integrate, I'm left with n times the integral of A mu, which is the gauge field on the d brane. And so that charge needs to be absorbed by the strings. All right. So we have that this vertex, so the baryon vertex is a d5 brane wrapped on S5. Okay, so I also now told you already how to deal with external quarks. I just consider external quarks means of infinite mass, and that means I take this string with one endpoint at infinity and one point in AdS. Then the string has infinite length, so its mass is the length times the tension. It's also infinite. So so that's the way to consider external quarks. So these external quarks, you can do things with them. So one of the things we could do, as we said, we can consider baryon vertices. But another thing we can do is, since they're infinite, we can just say that they define some, their motion defines some contour in the field theory, right? They're infinite mass, so we cannot move them by using any of the fields in the theory. So the contour is arbitrary. We write it as we want, and it will not be affected by the theory. So then we consider the contour the one that defines a Wilson line. So something like this. So you say, well, I just have some, and let me take quark and anti-quark. And we say, well, they're infinite, they just go on these straight lines, right? And perhaps if these are sufficiently long, I can just connect them by some short line up and down. So what will this give me? Well, this will give me a contour for a Wilson line or loop. So now let's see what that means. So a Wilson line is a path-ordered exponential of the gauge field. So if I have a path between x and y, then the Wilson line is the path-order exponential of the I times the integral from x and y to y of a mu dx mu. All right, or psi mu, I call it psi. Not to confuse. And so what does it mean to be path ordered? Well, the thing is, these things, the gauge fields, could be non-abelian, so their order matters. So then I cannot, so if the gauge fields are abelian, the path order doesn't matter, but if they are non-abelian, then their order matters, and by this I just mean I divide this into small paths and I take the product in the path order. So a mu psi n mu minus psi n plus 1 mu. Right? So that's a Wilson line. And you can see then that if I have, because it's a product of these exponentials, which transform, each of them transform in the gauge group, then, so each of them transform with let me call it, yeah, so e to the I. So this guy transforms as e to the a mu, the variation of a mu, which is d mu chi times the delta psi mu. So this gives the variation of chi, right? And I write it like e to the I chi of psi on one side and e to the minus I chi of psi n plus 1 on the other. And then when I do this, so I have a bunch of terms like this, and at each intermediate sites, this one will get cancelled by this one at site n plus 1. So the only thing that happens is that this transforms with e to the I chi of y to the left and e to the I chi of x to the right. Okay? And it's a way to define parallel transport, because then if I multiply, so if I take this Wilson line and I multiply by some scalar field in a fundamental, no, I have to call it something else, well, this phi, normal phi, then you see this normal phi of, let's say, x, right? Then this will transform with e to the I chi of x, so this will cancel this. And therefore, the Wilson line times the scalar field will transform with e to the I chi of y, which means I have effectively parallel transported the scalar from x to y. So this is the Wilson line, but the most important thing is the Wilson loop. Which is trace, so I call it W of C, which is trace of phi, where the endpoint and the starting point are the same. Because then, so first, if the endpoint and the starting point are the same, transforms, yeah, this is minus here, sorry. So e to the I chi of x to the left, e to the minus I chi of x to the right, but I take the trace, so the order doesn't, I mean, I have cyclical permutation inside the trace, so I can cancel this with this, which means that this is, Wilson loop is invariant. So the Wilson loop being gauge invariant, that means it's an observable. All things that are gauge invariant are observables. So you can see this a little bit more clearly because, so, well, first of all, the gauge invariant part, as I wrote there on page 140, if you take the abelian case, just by the Stokes theorem, so in the abelian case, phi c is e to the I integral over the closed contour C, which is the boundary of some other contour sigma, a d psi. And then by the Stokes theorem, this is the integral over the sigma of dA, which is f. So that's obviously gauge invariant. But in the non-abelian case, that's you get something similar, but not quite. If you consider this small square, so this was true for any closed curve and any bounded surface. But if for the non-abelian case, I have to consider only a tiny square, and in that case, I still get exponential IF plus corrections now. But then if I take the trace, and I get therefore the Wilson loop, then the Wilson loop contains trace f mu squared. And trace f mu squared is the action. Okay? So that's clearly something invariant and moreover something that could in principle be observable. Okay, so the Wilson loop is an observable, and I said, well, the one interesting Wilson loop would be this one, because the two parallel lines correspond to just two heavy quarks, well, a quark and an antiquark moving upwards in time, so this would be time. And then I just connect this with a tiny bit here, and then I make a loop. And so I can calculate this Wilson loop for this contour C. And now this should be an observable. And it's kind of clear what the observable should be when I think that this is, so this is a length r, and this is a time t much greater than r. So what does this correspond to? I have a quark and an antiquark, which, because they're infinitely heavy, don't move, but they can still feel a force between themselves, even if they don't move. So a force and therefore a potential. So this Wilson loop for the for this particular contour is defining for us the quark-antiquark potential. Okay, defines the quark-antiquark potential. And well, you could prove this a bit, I mean, not very rigorously, but it can be proven that this vacuum expectation value of this, so up to now this is an operator, but I can take the vacuum expectation value, that this is proportional to, well, we can see what's supposed to happen. I mean, this is exponential of things. So we've seen there that we got 1 plus the, in the case of a small contour, we got basically 1 plus the action S, right? Plus higher orders. So so you can think of this as also basically exponential of the action. And moreover, since this is finite, it has to be exponential of the minus action. And the action in this case for a static situation with quark-antiquark, right, would be just the time, integral over time, times the potential. So this is basically, I mean, a very hand-wavy explanation, but you can do this more precisely. Okay, and what happens in interesting cases? Well, the most interesting case is QCD, obviously. And in QCD, people have found on the lattice, and it was an expectation also that this is approximately a constant times R. This would be a confining potential because it means there's a constant force. The derivative of the potential with respect to the distance is the force, and it's constant. And this is called a string tension, QCD string tension. And the way to understand this, well, I didn't. This time I didn't draw it very well there. So the idea of the confining potential is as follows. So for the confining theory, the flux lines will be confined. And so all of them, even if they start off in some other direction, eventually they all are confined to this flux tube. Okay? So they're confined into a tube of a constant area. And so when you, let's say this is quark, this is antiquark. So when you take these apart, you just make this flux tube longer. And the flux tube has some constant energy density. So that gives you a linear potential. But so this is what we would like to see. This is the thing for QCD. But the thing for n equal 4 super Young males is different. So n equal 4 spare mills is conformal. So this is confining. But then we can have also conformal, which is what happens for n equal 4 spare mills. And conformal means that relative distances don't matter, right? Conformal means an overall scale doesn't matter, in particular. So if I have this, so if I have the Wilson line for this object, how do I make it such that the overall scale doesn't matter? Well, the only way it's possible for this contour is for the thing to depend only on T over R, right? That's the only possibility. But I said already that T appears this way, okay? So the only possibility is to have E minus T over R times the constant. And that means that in this case, VQQ bar, well, K. VQQ bar is K over R. Okay? And then people also give names to the behavior, to the total behavior of the, so the name is given for the total behavior of the Wilson loop VEV. And so for the confining case, this would be E minus T times R. And that is the area. So this is called the area law. And for both are confining, conformal. So for the conformal case, this is E minus T over R, right? And T, so the relevant thing here is T, which is very large. So I can write this as T plus R, right? I can even put a 2. And then, because R is much smaller than T. And then 2T plus R is just the perimeter. So this is the perimeter law. All right. Okay, so this was all about field theory. But how do I understand this in the gravity side? Well, we said what happens. We already said here. So we said that to get an external quark, an infinitely massive quark, what we do is we separate one of the original branes from the other ones. And the result is that I have a string that starts at infinity and ends somewhere in the middle, right? It's just that I'm interested in, so let me wipe this here. It's just that I'm interested in this contour. So I'm interested in, then this would be one quark, and this would be one antiquark. So this is one end of the string. Let me say it like this. But then this would be the opposite end of a string, right? So the natural thing to consider is that there is a continuous string that goes from one end to the other. And then what? And then this contour is in field theory. And we said the field theory lives at infinity. So I put this, yeah. I think I have a picture in here, that's slightly better. Yeah. Well, somewhat better. In page 143. So there is the contour that lives at infinity, and then the string moves, the string goes into the bulk and then comes back in. Now, first of all, why is this possible? Well, because in AdS space, gravity pulls you this way. So the string is pulled by gravity to go into AdS and then come back. You can see this because the so let's say I take this coordinate as x0. So x0 equal to 0 is infinity. Then the metric was this, right? And then that means that, so here I had minus dt squared plus this. The thing multiplying dt squared was 1 plus 2 u Newton. So u Newton goes like 1 over x naught squared. So the potential is very large at infinity and very small in the middle, which means the thing falls to the middle, okay? Okay. Yeah, then, as we said, the mass is 1 over the mass of a string is 1 over the tension, which is 2 pi alpha prime, times the distance, which is r in this case. But r of alpha prime is u, so this is u over 2 pi. Okay. And yeah, so yeah, I told you about the gravitational potential. Let's see, blah, blah. Yeah, okay, the rest I don't need to explain more. Okay. But now let's think, sorry, yeah, I actually need, sorry. So the, when I take one brain and take it apart, so then I'm left here with un minus 1 and here with u1. The string that has one end on the other, one end on one end on the other, from the point of view of the total gauge theory, it looks like a W boson. A W boson is a massive vector that was an original vector that was Higgsed and therefore gained a mass. So that's what happens here. You have a Higgs mechanism. By taking one brane away, we get massive states. And the string that goes between the two is has an expression of a W boson. But now, if we consider this picture, to get the potential, we need what? Well, so this action is actually infinite. We talked about this, that the on-shell action, when integrating all the way to infinity, becomes infinite. So this is not well defined. If I would take this action, in order to calculate from it the QQ bar potential, I would get something infinite. But luckily, that's not what we need, because what we need is to subtract. So the potential is when we subtract from the, I think I wrote it here, or maybe not. No. When we subtract from the whole energy, let me call, energy, minus the energy of the free W bosons. So what's a free W boson? Well, so initially I thought of this as just some string that stretches between the U1 brane and the UN-1 brane. So in this picture, I was thinking of it as just a straight string that goes from the infinity to some point in the middle. So, so the W boson would correspond to a string with a world sheet like this, just going straight down, and then so on all sides going straight down, right? So this would be parallelepiped. Okay. So I have to subtract. I have to subtract this. All right. So okay. So but why do I say that I need to consider the string action? Because the AdS-CFT prescription is that the vacuum expectation value of the Wilson loop, so this is supposed to be, so this is thought of like some sort of partition function. And so that depends on some boundary conditions for the field theory, the contour specifically. And so this should be equal to the partition function for the string now on the string theory side. And the partition function for the string with these boundary conditions is just to first approximation to the classical classical approximation. This would be just E minus S for the string, right? If we want to calculate further corrections, in principle, I would do a path integral in here, and that would result in fluctuations for the string, and I would have further corrections. But the 0th order calculation is just exponent minus the string action. Okay. So so W of C is minus E minus S string, but this was also equal to E minus T VQQ bar. So I have to have T VQQ bar of R equal to S string, right? And S string is T times the energy. And moreover, I want to have, so S string, but then S string, to subtract S string, let me call it straight. Let me put even yellow to be clear what I mean. So I have to subtract the action for this straight string. Okay. Now, one observation is that the Wilson loop that is being calculated with this action is actually not the standard Wilson loop that I've been describing until now, not this one, but rather a supersymmetric version of it. So the supersymmetric version of it contains also the superpartner that are still bosons, because the fermions in the VEV will give 0. So this refers to, so W of C here refers to not just path order exponential A mu dx mu, but also xi, did I call it theta I? Yeah, and dx mu. Oh, sorry, d tau for the particle. So, yeah, and here, this was also understood like this, in the sense that I integrate over the contour with a tau, and here I have a similar story. So, another reason would be to say that this is something that belongs to, so in the gravity dual, this is something that corresponds to AdS-5, and this is something that corresponds to X5. Okay. So we have two components, one gauge component, one scalar component to the Wilson loop, and they correspond to motion in AdS-5 and S5. It's just that in the cases we're interested in, we will consider the motion on S5 to be trivial, fixed point. So in that case, we will not worry about that. But in principle, we can consider more general things. Yeah. But the point is that this is the full Wilson loop that is that corresponds to the string world sheet. Okay. Okay. Yeah. Yeah, I mean, that's one way of saying it, but the point is that in principle, S5, could have been, we can still consider motion on S5, right? So it's not that we can never consider motion. We can consider. So I'm just saying that for the case that we're interested in, for the Wilson loop that we're interested in, this is considered to be constant. But we can, in principle, consider non-trivial Wilson loops that have also motion on S5. So it's not, so it's a choice for us. And the point is, we have to remember that this is not the standard, so the corresponding to the string world sheet, it's not the standard Wilson loop, but rather this supersymmetric Wilson loop. Yeah. Then to calculate the Wilson loop, well, I mean, this is not. I mean, I guess the details are not terribly important, but one thing we can say a few things. So The first is, you can see these small endpoints don't really matter because the time direction is much larger than the spatial separation. And so if I draw the string, well, I'm not very good at this, but you can try to imagine this string that it's roughly translationally invariant in T. So if I really don't need to consider the endpoints, I could just consider a string that looks everywhere the same. So it's approximately translation invariant. So that is the ansatz that one considers to calculate this of a translation invariant in the time direction, a string in the time direction. And so the only variable that one has is u of x, where x is the spatial direction that separates the quark and the anti-quark. And so then one considers the string for the the string action on this one-dimensional path, depending only on u of x, and one obtains the formula over there in the page 145, which is so S string is T over 2 pi integral square root dx u squared plus u4 over r4. And then one finds the implicit solution for x depending on u and u0, or you can say x depending on u over u0 and u0. And just because the coordinate y is u, which is u over u0, is dimensionless now, so it's easier to deal with it. And then we obtain also the result written there. So x is a so r tilde squared over u0 times an integral from 1 to u over u0. And since x is the spatial separation centered in the middle, so this would be x, then I put x equal to L over 2, and then I get the quark-antiquark potential. So L is L over 2, then becomes r tilde squared over u0 times some numbers. And so that allows us to calculate, to relate L to u0, or u0 to L, if you want. So this integral is still becomes infinite when u goes to infinity. But as we said, once we subtract the straight string, then we get rid of that divergence. And so that was what was done there on in formula on page 145. And so one gets that T V Q Q bar of L is T times 2u0 over 2 pi times something that that gives now is not divergent anymore and just gives a number. And then finally you relate u0 to L, and so you get that V Q Q bar is is so minus square root g squared 2g squared Young minus n over L times some number which is 4 pi squared over gamma 1/4 squared. So the observation, the only observation that I want to make is that this is a very non-perturbative result. So it's square root of the effective 't Hooft coupling. So that cannot be obtained by any power law, right? It's non-perturbative. And otherwise is conformal. The QQ bar is defined, is 1 over the length. So it's conformal as expected, and there's some prefactor that has been calculated. Yeah, so a final observation about these Wilson loops is that Alday and Maldacena in 2007 have also defined the gravity dual of the regular Wilson loop, the non-supersymmetric one, which amounts to putting Neumann boundary conditions instead of Dirichlet, instead of fixing the string, on the S5. So, yeah. Okay, so let me go now to brain probes in AdS-CFT. So until now, we've seen that solitons are mapped to some solitonic brains in AdS-CFT. But solitonic brains are heavy. But we can consider a moving brain that is a probe, which means it's so light that it doesn't affect its background. And then, if I consider the motion in the radial direction u, remember that the radial direction u corresponded to energy. So a probe brain moving in u probes different energies in the gravity dual. Different energies in field theory by moving in the gravity dual. Of course, that has only meaning in a non-conformal theory. And moreover, so one probes the theory, but in particular, you can consider the excitations of the brain, its fluctuations. And its excitations correspond to mass spectra for fluctuations in the field theory, which are also considered at various energies. So if I consider scalar fluctuations, those are mesons, like the pion. If I consider vector fluctuations, those are vector mesons. So, and also, we can also find baryons. We can also understand baryons as a solitonic solution of the probe brain. So the probe brain is a very important tool, but you have to remember that it's not exact. Being a probe, it means it's not really part of the gravity dual, doesn't affect it. So it's an approximation. Yeah, and the motion in U, as we said, is corresponds to RG flow, or motion in energy. And this RG flow, or motion in energy, will affect the various hadrons, will affect the various mesons and baryons, and that corresponds to the change in mass spectra on the brain. Okay, So now let me say some things also about a different kind of probe, not a brain probe, but rather probing with wave functions. The reason why I do this is because the next lecture will be somewhat related to that. Yeah, so perhaps, are there questions at this moment? Yeah. The probe brains? That's right. So the probe brains solve the equations of the probe background, not of the full background. Yeah. All right. Okay. So we'll consider now the the scattering of wave function. So the scattering in the gravity dual and what it corresponds to in the field theory. So first, as we said, the most interesting thing is for us is QCD. And QCD is, like any theory, is conformal in UV at high energies. So that means that it's the gravity dual, or would-be gravity dual of QCD should be AdS-5 at large cross X sum X5 at large R. But I also said that if we want to have a mass gap like we have in a real QCD, we need to consider the space ending at some minimum R. So mass gap, that means some R minimum. And the simplest thing is to be just a straight cutoff. I mean, there are other things one considered. We considered last time finite temperature, but the simplest is just to take AdS-5 and just cut it off at some R minimum. And then, because because the momenta, so if I write AdS, the AdS metric as R squared over R squared dx squared plus R squared dr squared over R squared. So because of this factor, that means that momenta in QCD P mu are related to momenta in 10 dimensions via the inverse factor, because the momentum goes like 1 over dx. But a characteristic momentum scale for 10-dimensional for the 10-dimensional theory is of the order of 1 of the AdS scale, which means that in QCD I have characteristic scale of R over R squared. And the characteristic QCD scale on the other hand is lambda QCD, the the scale that gives, for instance, the masses of the glue balls. Which means that I must have that R minimum, the minimum cutoff associated to a mass gap, must be related to lambda QCD by this formula. R minimum is R squared lambda QCD. Okay, so this is the simplest model known as hard wall, because really we have a hard cutoff or a hard wall. We just cut off AdS-5 at R minimum. And then let's consider in this model, let's consider scattering corresponding to scattering of mesons or glue balls. So this would correspond to scattering of some states in some states that couple to the operators, to the meson or glue ball operator. And we already said that there's a map between wave functions. So if I have e to the I kx in field theory, then I would have e to the I kx times a wave function of the extra dimensions. So then the ansatz for scattering in the gravitational theory that corresponds to scattering of the mesons or glue balls is by Polchinski and Strassler in 2001. And it involves the assumption that we have a local scattering in gravity, which is a sensible assumption. And then the only thing that could happen is that we have a convolution of the amplitude for scattering with these extra wave functions, right? So the prescription then is a QCD, depending on momenta pi, is, so we have the string theory scattering depending on momenta p tilde I, right? And then I have to add this extra wave function for the extra directions, right? So product over I psi I, so R omega tilde x5, and then integrate obviously over these extra dimensions. dr d5 omega 5 squared minus g. So one interesting object is we can define the analog of the string scale by so we can define the analog of the string scale in the QCD theory, in the, well, field theory that is QCD-like, so QCD string scale. Alpha prime with a hat was defined such that momenta in QCD, momenta in QCD in this string in this QCD string units are greater or equal than momenta in string theory in string units. And momenta sorry, yeah. Yeah, this is P tilde, and P tilde was R, capital R over R, P mu. So capital R over R. Yeah. And I've done something wrong over there. I cannot see what, but anyway, I have the relation between lambda QCD and R minimum, and I also know that R squared is square root G squared N with in units of alpha prime. And so I wrote something wrong there on the page 148, but the point is once you do this, you obtain uniquely the definition of alpha prime hat as 1 over square root G squared N times 1 over lambda squared, lambda QCD squared. Okay. And we could also define the analog of a Planck scale and Planck hat by the same relation, so the same relation without the hats to the string scale. So GS minus 1/4 alpha prime hat minus a half. So if I would remove the hats, I would have the relation between the Planck scale and the string scale in string theory. And then this becomes n to 1/4 lambda QCD. All right, so what kind of behavior do we see in field theory knowing the behavior of string amplitudes? So one can consider the string amplitude for scattering, for 2-to-2 scattering. And okay, it's a rather long formula written page 149. And one considers it in the limit of alpha prime S much greater than 1 and alpha prime T fixed, where S and T are the Mandelstam variables. S is center of mass energy squared. And then one sees that this A string behaves like alpha prime S to the power alpha prime T over 2 plus 2 with something in front. And and then by putting this, so this is known as the Regge limit. And by inputting this into the Polchinski-Strassler formula, and noting that the integral is dominated by R minimum, I mean, looking at the form of the integral and seeing that it's dominated by R minimum, you find basically that AQCD has the same behavior. So one finds that AQCD goes like, so there's a function of T, and then alpha prime hat S to the power 2 alpha prime hat t over 2 plus 2. And this is known as Regia behavior in QCD, and it's usually very hard to obtain directly from a model. So the fact that you have a function of t times s to a function of t. All right, so that means that Regia behavior is obtained in string theory, is obtained from string theory in the gravity dual. Okay. So let me say a few more words about this scattering. So now if we consider scattering at higher and higher energies, eventually, so if you have in a gravitational theory and an object and you give it more and more energy, eventually it will start to look like a shock wave, like a gravitational shock wave, something that moves at the speed of light and is concentrated on the light front. So this would be something of the type that we call a parallel plane or PP wave. So this is something that generically is of this form, 2dx plus dx minus plus h of x plus xi dx plus squared plus dx dxi dxi. And the interesting thing about this PP wave is that it's an exact solution of the Einstein equation. And it has a point-like source. It has a point-like source. So one considers, one calculates the Ricci components for this metric, and you find that the only non-trivial component is r++, and specifically this becomes just di squared h with a -1/2 in front. And that's doubly interesting because not only I have just one component, but more importantly, this is linearized. So there are no nonlinear terms here, right? It's a linearized term, so it means that the linearized solution is actually exact. And if I use the Einstein equation, and I consider a point-like source, specifically, I say this is 8 pi g Newton p, and then delta in the xi directions and delta in x plus. Then the solution, so first, because I consider delta of x plus, the same thing happens for h. H is also a delta of x plus. And, or I call it phi here, okay. Phi of xi. And then, I can consider various dimensions. This is just a harmonic function. So for d equal to 4, harmonic function in the transverse directions. So for d equal to 4, I get log transverse direction squared. For d greater than 4, I get 1 over rho to the d minus 4. Momentum, right? It's a light-like particle, so it's defined only by momentum. So if we consider, then as I said, you consider a particle moving sufficiently fast, it becomes eventually a shock wave of this type with a delta of x plus and a certain wave function phi. And so if you consider a collision of two particles, you can think of an intermediate regime where only one particle is a shock wave and the other one moves in this shock wave. That's the scattering. But eventually, when you get to center of mass energies of the order of Planck scale, so GNS of the order of 1, then you have to consider both particles being shock waves. And so before the interaction, you can consider this kind of interacting thing where I considered adding here also, so this would be H1, I guess. Yeah, I didn't put delta of x plus. Okay, so yeah, so now I would have delta of x plus phi 1, and then I would have another with delta of x minus phi 2 dx minus squared. And that's obviously not a solution anymore everywhere. It's only a solution before the collision, which happens at x plus equal x minus equals 0, right? Before that, they're not interacting. But when the two shock waves collide, suddenly it's not a solution anymore, right? This is linear, but this is linear in the presence of a single shock wave. When there are two, there's not linear anymore. And then Penrose and then later at Early and Giddings have proven that a so-called marginally trapped surface forms at the collision point. So a marginally trapped surface is a surface that that bends light in light that goes out in both future directed directions. So for, let's say, a Schwarzschild black hole, a marginally trapped surface is just the event horizon, but that's just a coincidence. In general, is not. So showing that there's a marginally trapped surface implies, by a general relativity theorem, that in the future of this collision, you find a black hole with an event horizon that that surrounds the trapped surface. So that means, in effect, they found that there is a black hole being formed in the shockwave collision, and specifically for non-zero. This happens also for non-zero impact parameter. And then, therefore, you can find a maximum impact parameter for this and say that the cross-section is just, the geometrical cross-section is just pi times this maximal impact parameter squared for black hole formation. And yeah, let's see. Yeah, it's too many things. I think I will not say this. Just want to show this picture on page 153 and say a few words now. So why this is important, this black hole formation? Well, so you might think that's the biggest, the last possible behavior, that you form a black hole. But no, the black hole also has a size, the black hole that's being formed. And so there are two intermediate regimes. There one regime where first you form a small black hole, then you form a black hole that fills the size of AdS, and finally you form, since you have a cutoff, you find a black hole that is now effectively on the cutoff, because we said that most of this scattering happens on the cutoff. And so looking at this picture on 153, you could say, I mean, this is a little bit more pictorially what I said. So you first create a small black hole in A, then in B you create a black hole that's, that is large enough. So first it fills AdS, but then it's large enough that's effectively on the cutoff at R minimum. And so when that happens, the black hole suddenly, so this was a quantum amplitude, but eventually this is so large and fixed that it becomes effectively a classical scattering, where we form a classical black hole on the brain. Anyway, so that's what I want to say, and I will not deal with the rest. And next time we'll talk about the PP wave correspondence. So, questions? Yeah. Let me give you this.
So on the regular QCD confining potential, now in principle, any positive power of the distance would be equally confining, right, beyond linear. So is linear just what comes out of the lattice, or can we already expect this just from QCD instead of quadratic?
Well, yeah, so so I think that, so initially there was just what's coming from QCD. I think by now people say that, there's only a small distance regime where that happens. So it was also what came out of this nice picture with the flux tube, right? And further, you wanted, I mean, the same idea, but you wanted a constant force. So, well, the point is, if these things, now if you have quarks in the theory, if you pull these apart, you will actually form quark, anti-quark pairs. And so this eventually will break. So, yeah, so the force increasing is not a good idea, and eventually this thing will break. And so, yeah, I think it's more on the lattice, in the case where you don't have quarks, that people consider this linear potential. Okay. Well, okay, so it's anyway, it's late, so we can leave the questions to the question session, and I'll see you at 1.